Did you know there's a planet where it rains diamonds? Not in some far-off sci-fi fantasy, but right here in our own solar system. Neptune and Uranus, those icy giants spinning in the outer darkness, have atmospheres so intense they crush methane into glittering diamonds that fall like celestial hail. And that's just one of the countless wonders hiding in the cosmos, waiting to shake up everything we think we know. Space isn't just about empty blackness and silent stars. It's a wild, unpredictable frontier where the rules of Earth don't apply, and every discovery feels like stumbling into a cosmic magic show. That's exactly what we're diving into today. 30 of the weirdest, most mind-bending facts about space exploration that'll make you question reality itself. From astronauts growing taller in zero gravity to galaxies colliding in a slow-motion dance billions of years long, the universe is packed with surprises that defy logic and ignite our imagination. Think about this. Right now, as you're watching this, there's a spacecraft hurtling beyond our solar system carrying golden records of human voices and music, a message in a bottle tossed into the cosmic ocean. It's proof that space isn't just a scientific playground. It's the grandest stage for human curiosity, where every mission rewrites the story of what's possible. So buckle up. We're about to take a whirlwind tour through the quirks and marvels of space exploration, where the mundane gives way to the miraculous, and even the smallest detail can leave you awestruck. Whether you're a seasoned stargazer or someone who's never peered through a telescope, these facts will remind you that the universe is stranger, funnier, and more wondrous than we could ever invent. Ready to have your mind blown? Let's launch. Ever notice how astronauts seem to float effortlessly in videos from the International Space Station? That weightlessness isn't just fun, it's literally stretching them out. Without Earth's gravity pulling down on their bodies, the spine's vertebrae relax and expand, adding up to 3 inches of temporary height. Imagine waking up taller just by leaving the planet, no miracle growth serum required. Here's the catch, that extra height isn't a free upgrade. The spine isn't meant to stay elongated like that. Back on Earth, gravity squashes everything back into place, often causing intense pain as compressed nerves and muscles readjust. Some astronauts compare it to the ache of a bad growth spurt, but compressed into days instead of years. Even simple movements become agonizing until their bodies relearned how to handle Earth's relentless pull. Scientists call this spinal unloading, and it's not just a quirky side effect, it's a serious challenge for long-term space missions. If a trip to Mars takes months, astronauts could arrive with weakened backs, making strenuous tasks riskier. That's why NASA studies this phenomenon obsessively, using ultrasound scans and posture-tracking suits to map every millimeter of change. The goal, designing exercises and suits that mimic gravity's pressure, keeping spines strong even in the void. But there's a silver lining. Understanding this could help Earth-bound patients too. Research on spinal fluid shifts in microgravity is giving doctors new insights into back pain and disc injuries down here. So next time you see an astronaut floating gracefully, remember they're not just exploring space. They're helping us unravel the mysteries of our own bodies, one stretched vertebra at a time. When astronauts first stepped onto the moon's surface, they expected silence, emptiness, maybe even awe. But no one warned them about the smell. After clambering back into the lunar module and peeling off their helmets, Apollo crews were hit with an unexpected scent clinging to their suits: gunpowder. Not the faint whiff of a distant fireworks show, but the sharp, metallic tang of spent bullets, as if they'd rolled in the aftermath of a battlefield. Buzz Aldrin described it as wet ashes, while others compared it to burnt charcoal or the acrid sting of a just extinguished match. So why does the moon, a place with no air, no fire, no life, smell like a shooting range? The answer lies in lunar dust, that fine, clingy powder coating the surface. Back on Earth, smells travel through air, but moon dust chemically changed when it met the astronaut's oxygen-filled cabin. Solar radiation bombards the lunar surface relentlessly, charging the dust with energy. When astronauts brought it inside, those charged particles reacted with moisture in the air, releasing that bizarre gunpowder aroma. But here's the real kicker. That dust wasn't just stinky, it was mysterious. Apollo crews reported it stained their gloves gray, clogged equipment joints, and even irritated their throats when tiny particles snuck into the cabin. Some scientists think it might be dangerously sharp, like microscopic shards of glass forged by eons of meteorite impacts fracturing the rock. Future lunar colonists might need airlocks with dust vacuuming systems just to keep their habitats clean, or risk tracking in a gritty, gunpowder-scented mess after every moonwalk. And that scent, it's a haunting reminder of how alien the moon truly is. Earth's atmosphere erodes rocks into soft sand, but lunar dust is raw, unfiltered by wind or water, a 4.5 billion-year-old fossil of cosmic violence. Every whiff brought home by astronauts was a breath of pure, untouched history, carrying echoes of the solar system's chaotic birth. So next time you catch the sulfurous bite of a blown-out candle, think of the moon, where the very ground smells like the aftermath of creation itself. You might think space would echo with the roar of rocket engines or the explosive bursts of colliding galaxies. After all, that's what every sci-fi movie shows us. But the reality, it's quieter than the deepest corner of an abandoned library. In space, no one can hear you scream, and that's not just a clever tagline, it's physics. Sound waves need something to travel through, whether it's air, water, or even solid ground. But out there in the vacuum between stars, there's no atmosphere, no molecules to vibrate and carry those waves. The result, utter, overwhelming silence. Imagine floating next to a supernova, the most violent explosion in the universe. You'd see a blinding flash, feel the heat ripple across your skin, but the actual detonation. Not a whisper, no thunderous boom, no shockwave rattling your bones, just eerie stillness. It's why astronauts rely so heavily on radio signals. Without them, they'd be cut off from every sound, even the voices of their crewmates just inches away. This silence has fooled filmmakers for decades. Think of Star Wars' iconic dogfights with TIE fighters screeching through space like angry wasps, or the deep, ominous hum of a starship's engine in Star Trek. Those sounds are thrilling but completely impossible. Directors add them because our brains crave noise to make sense of motion. Remove the soundtrack from a space battle, and suddenly it feels hollow, unnatural. Yet that's the truth of the cosmos, a vast, soundless stage where entire stars live and die without making a peep. But here's the twist: silence isn't just absence. It's a clue. Scientists study the lack of sound waves to map the universe's structure, using the stillness to detect subtle gravitational ripples or the faint echoes of cosmic background radiation. And for astronauts, that quiet is a constant companion, a reminder of how fragile our connection to Earth really is. Floating in the void, surrounded by nothingness, the only sounds you'll hear are the ones you bring with you, the beep of equipment, the rush of your own breath inside your helmet. It's lonely, beautiful, and humbling all at once. So next time you watch a spaceship roar across the screen, smile, and remember the universe's best-kept secret. It's always listening but never answering. Most planets in our solar system spin like graceful tops, rotating counterclockwise as they orbit the sun, but Venus, it's the cosmic rebel, spinning backward with a rotation so sluggish. A single day there lasts longer than its entire year. While Earth whips around its axis every 24 hours, Venus takes a staggering 243 Earth days to complete one rotation, and it does it clockwise, defying the rhythm of nearly every other planet. If you could stand on its surface, which you absolutely couldn't, but we'll get to that, the sun would rise in the west and set in the east, crawling across a sky choked with sulfuric acid clouds. So what flipped Venus upside down? Scientists still debate the culprit, but the leading theory is a colossal collision. A planet-sized slam early in the solar system's history that literally knocked Venus off its axis. Another possibility, gravitational tug-of-wars with the Sun's thick atmosphere, slowed its spin over eons until it reversed direction entirely. Whatever the cause, the result is a world that feels ripped from a sci-fi nightmare. Its surface temperatures hit a blistering 860 degrees Fahrenheit, hot enough to melt lead, while atmospheric pressure crushes down 92 times harder than Earth's, equivalent to being a mile underwater. And here's the twist: Venus isn't completely alone in its backward spin. Uranus rolls around the Sun like a drunken barrel, tipped sideways at 98 degrees, likely from another ancient impact. But Venus remains the true oddball, spinning opposite not just its planetary neighbors, but the very fabric of the solar system's birth. Some astronomers joke it's the goth kid of the cosmic family, brooding, mysterious, and determined to do things its own way. Yet this backward dance isn't just a curiosity, it's a cautionary tale. Venus started out eerily similar to Earth, with oceans and a temperate climate. But a runaway greenhouse effect turned it into a hellscape, proving how delicate planetary balance really is. Studying its retrograde spin helps us piece together the solar system's violent youth and serves as a stark reminder: even small cosmic quirks can have world-ending consequences. So next time you watch a sunset, imagine it happening in reverse and thank your lucky stars you're not on Venus, where the sky moves backward and the ground burns like a forge. Deep in the heart of our galaxy, floating among the stars of the Sagittarius constellation, there's a cosmic party happening, one with enough alcohol to fill thousands of Earth's oceans. Meet Sagittarius B2, a colossal molecular cloud stretching over 400 light-years across, packed with billions of liters of ethanol. That's right, space isn't just full of rocks and gas. It's home to the largest known bar in the universe, where the drinks are free and the glasses are light-years wide. But before you imagine interstellar bartenders serving up galactic margaritas, let's break down what this actually means. Sagittarius B2 isn't a floating cocktail. It's a dense, frigid cloud of molecules, including ethyl alcohol, the same stuff in your favorite beer or whiskey. The ethanol here isn't liquid, it's vapor, mixed with other complex organic compounds like formaldehyde and acetic acid. Scientists estimate this cloud contains enough alcohol to supply every person on Earth with 300,000 drinks a day for billions of years. Talk about happy hour on a cosmic scale. So how did this gigantic boozy cloud form? It's all about chemistry in the extreme cold of space. In the frigid vacuum between stars, simple atoms like carbon, hydrogen, and oxygen cling together on the surface of dust grains, slowly building into more complex molecules. Over millions of years, radiation and shock waves from nearby supernovas provide the energy to rearrange these atoms into ethanol and other organic compounds. It's like a slow-motion distillery where the universe itself is the brewer, patiently crafting molecules in the darkness. And here's the real kicker: Sagittarius B2 isn't just a curiosity, it's a gold mine for astrochemists. This cloud is essentially a sprawling laboratory for studying how the building blocks of life form in space. Many of the molecules found here, like ethanol and glycolaldehyde, a simple sugar, are precursors to amino acids, the stuff our own bodies are made of. Some researchers even speculate that clouds like this could have seeded young planets with the ingredients for life, raining down organic material on primordial Earth billions of years ago. But don't get too excited about harvesting this cosmic keg anytime soon. Sagittarius B2 sits 26,000 light-years away, wrapped in a haze of deadly radiation near the supermassive black hole at our galaxy's center. Even if we could reach it, the alcohol isn't exactly drinkable. It's laced with toxic chemicals and spread so thin that scooping up a single shot would require sifting through cubic miles of space. Still, this cloud reminds us that the universe is far more chemically inventive than we ever imagined, turning the void between stars into a factory for the very molecules that make life possible. So next time you raise a glass, remember, somewhere out there, the cosmos is toasting right along with you. Mercury plays by its own rules when it comes to time, so much so that a single day on this scorched little planet lasts nearly 2 Earth years. While we're used to sunrises and sunsets ticking by like clockwork, Mercury's dance with the sun is a bizarre, lopsided waltz. It spins so slowly that one full rotation, a day in the traditional sense, takes a staggering 59 Earth days to complete. But here's where things get truly strange, because Mercury also orbits the Sun at breakneck speed, its solar day. The time from one sunrise to the next stretches out to a mind-bending 176 Earth days. That means if you stood on its surface and somehow survived the 800-degree temperature swings, you'd witness just 2 sunrises over an entire Mercurian year. This cosmic time warp happens because of something called orbital resonance. Mercury's rotation isn't random, it's locked in a precise gravitational tango with the Sun. For every 2 orbits it completes around our star, the planet spins exactly 3 times on its axis. Scientists call this a 3-to-2 spin-orbit resonance, and it's like nothing else in our solar system. Picture a ballerina twirling while circling a spotlight. She spins at a fixed rhythm to keep facing the same direction during each pass. Mercury does something similar, but with a twist, literally. The side effects of this slow-motion day-night cycle are extreme. One hemisphere bakes under the sun's relentless glare for months, reaching temperatures hot enough to melt zinc, while the opposite side plunges into a deep freeze colder than Antarctica. And because Mercury has almost no atmosphere to trap or distribute heat, these extremes hit like a sledgehammer. Shadows on the planet's surface can be sharper than a razor, and the terrain itself creaks and cracks as it expands and contracts under the brutal thermal whiplash. But why does Mercury spin like this at all? Blame the sun's gravity. It's so overpowering this close in that it warps space-time itself. Early in the planet's history, the sun's tidal forces likely slowed Mercury's rotation until it settled into this odd, locked rhythm. It's a stark reminder of how much our familiar earthly cycles, 24-hour days, predictable seasons, are just one way a planet can experience time. Out there in the cosmos, the clock ticks to a far stranger beat, and here's the kicker: Mercury's resonance isn't just a curiosity, it's a cautionary tale for astronomers hunting planets around other stars. If a world like this can exist so close to its sun, what other wild timekeeping quirks might be hiding in distant solar systems? Every probe we send to Mercury peels back another layer of its mysteries, proving that even the smallest planets can rewrite the rules of time itself. So next time you check your watch, remember, somewhere out there, a day can last longer than a lifetime. The sun seems like a familiar presence, a bright disk in our sky, warming our days and guiding our seasons. But peel back its glowing surface and you'll find a monster of almost unimaginable scale. At its core, the sun could swallow 1.3 million Earths whole with room to spare. Picture this: if our entire planet were a single grain of sand, the sun's core would be a beach stretching farther than the eye could see. That's not just big, that's cosmically enormous. What fills all that mind-boggling space? A non-stop nuclear inferno. Every second, the sun's core smashes together 600 million tons of hydrogen, fusing it into helium under pressures so extreme that atoms scream in protest. The temperature here hits a blistering 27 million degrees Fahrenheit, hot enough to vaporize diamonds like morning dew. And this isn't just random chaos, it's a precision-engineered furnace running non-stop for 4.5 billion years with barely a hiccup. To grasp how this works, imagine the core as the ultimate pressure cooker. Gravity crushes hydrogen atoms so tightly they stop behaving like polite particles and start merging in a process called nuclear fusion. Each collision releases a burst of energy tiny on its own, but add up trillions per second, and you've got enough power to light up the entire solar system. The crazy part, all that energy takes thousands of years to fight its way to the surface, bouncing between atoms in a slow-motion game of pinball before finally bursting free as sunlight. Here's where things get even wilder. Despite its staggering size, the Sun's core is incredibly dense. The matter here is packed so tightly that a teaspoon of it would weigh as much as an elephant here on Earth. Yet paradoxically, it's this crushing density that makes fusion possible, forcing atoms close enough to overcome their natural aversion and stick together. But don't let the numbers numb you to the sheer weirdness of this place. The core isn't just a ball of fire, it's a cosmic alchemy lab, turning the simplest element in the universe into the energy that fuels life itself. Every breath you take, every leaf that grows, every drop of rain owes its existence to those distant nuclear reactions. And when you realize that the sunlight touching your skin right now began its journey centuries ago, trapped in that seething solar heart, it's hard not to feel a little starstruck. So next time you squint up at the sun, remember, you're not just looking at a bright spot in the sky. You're glimpsing the engine room of our solar system, where impossible scales and unfathomable forces keep the cosmic lights on. And somewhere in that churning, million Earth-sized core, the universe is quietly turning hydrogen into stardust, one atom at a time. If Earth rotated as fast as a neutron star, you'd be flung into space before you could blink. These cosmic powerhouses, forged in the apocalyptic fury of supernova, spin so fast they blur the line between physics and science fiction, some completing 600 full rotations every single second. That's not just quick, it's impossibly fast, flinging material around at nearly 1/3 the speed of light. The surface of a neutron star moves so rapidly that if it had mountains, they'd be sanded down to atomic smoothness in seconds by the sheer centrifugal force. So how does something so extreme even form? Picture a massive star far larger than our Sun running out of fuel in its final act. Without the outward push of nuclear fusion to balance gravity's crushing grip, the star collapses inward in a cataclysmic explosion called a supernova. What remains isn't just a remnant, but a celestial zombie, a neutron star. All that star matter gets compressed into a sphere no bigger than a city, yet weighing more than our entire Sun. A single sugar cube-sized chunk of this material would weigh 1 billion tons on Earth, as much as a mountain range squeezed into a teaspoon. But the real magic happens when this ultra-dense object starts spinning. Like an ice skater pulling in their arms to spin faster, conservation of angular momentum takes that original star's slow rotation and whips it into a frenzy during collapse. The result, a pulsar, a neutron star beaming radiation like a lighthouse from its magnetic poles. When those beams sweep across Earth, we detect them as precise, rapid-fire pulses of radio waves, some ticking with a regularity that rivals atomic clocks. Astronomers once mistook these signals for alien broadcasts, dubbing the first discovery Little Green Men 1, until the truth proved even stranger. What's wild is these speeds aren't just for show, they warp spacetime itself. The intense gravity and rotation create frame-dragging effects predicted by Einstein, where the star literally twists the fabric of the universe around it. And the limits are still being pushed. The fastest known pulsar, named PSRJ 1748-2446 AD, spins at an eye-watering 716 times per second. At that rate, the equator is moving at an unbelievable 1/4 light speed, stretching physics to its breaking point. Yet neutron stars aren't just cosmic oddities, they're laboratories for the universe's most extreme conditions. Studying them helps scientists test the laws of physics under pressures and densities impossible to recreate on Earth. Some even think quark stars, hypothetical objects even denser than neutron stars, might lurk among the fastest spinners where matter itself breaks down into exotic particles. So the next time you glance at the night sky, remember, hidden in the darkness are natural particle accelerators spinning silently at speeds that rewrite the rules of reality. Up in Earth's orbit, there's an invisible minefield racing around our planet at speeds that make bullets look slow 17,500 miles per hour. That's how fast space junk tears through the void, turning even a fleck of paint into a potential cannonball. In fact, that tiny paint chip is exactly what cracked the windshield of Space Shuttle Challenger in 1983, leaving a pit the size of a quarter. But today, the problem has exploded into something far more terrifying. Over 100 million fragments of debris now circle Earth, from abandoned satellites to spent rocket boosters, all moving 10 times faster than a high-powered rifle shot. The most chilling example, February 10, 2009, when a defunct Russian Cosmos satellite slammed into an active American Iridium communications satellite over Siberia. The collision didn't just destroy both spacecraft, it shattered them into 2,000 new pieces of shrapnel, each capable of obliterating another satellite. Imagine two cars crashing on a highway, except they're moving at hypersonic speeds, and their wreckage spawns thousands of additional deadly projectiles. That single accident increased orbital debris by 10% overnight, creating a ripple effect that still threatens satellites today. Here's what makes space junk so deadly. At those velocities, kinetic energy rules. A 1-centimeter bolt carries the same punch as a mid-size sedan going 60 miles per hour. The International Space Station routinely dodges chunks big enough to puncture its hull, while astronauts in the cupola module sometimes spot debris zipping past like lethal fireflies. Even the tiniest fragments, things as small as a screw, can disable critical systems, as ESA's Sentinel-1, satellite, learned in 2016 when a millimeter-wide particle cracked its solar panel, leaving a jagged scar visible from onboard cameras. But the real nightmare scenario is Kessler syndrome, a chain reaction where one collision triggers more, eventually encasing Earth in an impassable shell of shrapnel. Scientists warn we're already close. Certain orbits now resemble a cosmic shooting gallery, with operators constantly maneuvering satellites out of harm's way. The U.S. Space Surveillance Network tracks objects as small as a baseball, but millions of untraceable scraps still lurk unseen. Solutions range from the poetic to the bizarre. Japan's JAXA tested a magnetic space whip to corral debris, while startups propose giant nets or harpoons. ESA's Clear Space mission aims to launch a 4-armed robotic janitor to grapple dead satellites. But the best hope might be prevention, new satellites designed to deorbit themselves, burning up safely in the atmosphere. Until then, every new launch risks adding to the cascade, turning humanity's greatest achievement, our reach into space, into a trap of our own making. So next time you gaze up at the stars, remember, the real danger isn't just what's out there, it's what we've left behind, hurtling overhead at speeds no shield can fully stop. The final frontier is becoming a junkyard, one collision at a time. Tears don't fall in space, they cling. Imagine floating inside the International Space Station, feeling that familiar sting of emotion welling up, only to discover your tears have other plans. Instead of streaming down your cheeks, they gather into wobbly, quivering globes that stick to your face like tiny liquid marbles. Astronaut Chris Hadfield demonstrated this during his time on the ISS, showing how a single tear can pool in the corner of your eye, growing larger and larger until it finally detaches as a floating sphere, refracting the cabin lights like a miniature crystal ball. This bizarre behavior happens because gravity isn't there to pull the tears downward. On Earth, gravity gives tears weight, guiding them in predictable paths as they trickle toward your chin. But in microgravity, surface tension, the same force that makes water bead up on a freshly waxed car takes full control. The result, tears don't fall, they coalesce, merging into surreal, free-floating blobs that drift until they collide with a surface or, as some astronauts have grimly noted, get inhaled if they stray too close to your nose. But here's the twist: crying in space isn't just visually strange, it's physically uncomfortable. Without gravity to drain them, tears can flood your eyes, creating a stinging, saline-heavy film that blurs vision until you wipe it away. NASA astronauts have reported that emotional moments in space feel different, almost unfinished, because the usual physical release of tears rolling down your face is replaced by this odd, suspended sensation. Some describe it as crying into a void, where the emotional catharsis feels incomplete without gravity's grounding pull. The science behind this phenomenon goes beyond tears. All fluids in space behave unpredictably. Sweat clings to skin in sticky layers. Coffee forms floating globs that can burn you if they escape the cup. And even a simple sneeze sends a mist of droplets hanging in the air like a miniature nebula. This is why space stations are designed with careful airflow to guide fluids away from astronauts' faces and sensitive equipment. Yet there's a deeper irony here. Tears are one of humanity's most primal, universal expressions, whether from joy, frustration, or homesickness. But in space, even this fundamental human experience gets remade by the absence of gravity. Astronauts have confessed that the weirdness of crying in orbit sometimes makes them laugh mid-sob, turning poignant moments into surreal comedies. It's a reminder that space doesn't just change how we move or eat, it reshapes how we feel, right down to the way our bodies express emotion. And perhaps that's the most profound lesson of all. Every tear shed in space carries more than salt water. It holds the tension between our earth-bound instincts and the reality of life in the cosmos. For all our technology and training, we're still creatures of gravity, wired to expect tears to fall. When they don't, it's a quiet reminder: out there, even our sorrows float. Jupiter's Great Red Spot has been the solar system's most iconic storm for at least 400 years, a churning, crimson maelstrom wide enough to swallow Earth whole. But this ancient tempest, once a titan stretching 25,000 miles across, is now shrinking at an alarming rate. When Voyager sped past Jupiter in 1979, the storm spanned twice our planet's diameter. Today, it's barely wider than one Earth, and astronomers aren't sure if it's dying or just transforming into something new. The first recorded observation of the Great Red Spot dates back to the 1600s, when telescopes were still a novelty. Astronomers like Giovanni Cassini noted a permanent spot marring Jupiter's striped atmosphere, likely the same vortex we see today. For centuries, it dominated planetary studies, a constant amid Jupiter's ever-shifting cloud belts. But by the late 20th century, high-resolution images revealed something unsettling. The spot was losing bulk. Measurements showed it shedding nearly 500 miles in width per year, its once oval shape now more like a crumpled rose fraying at the edges. What's fueling this decline? The storm survives by cannibalizing smaller vortices, drawing energy from Jupiter's violent jet streams. But changes in these wind patterns, possibly due to shifting temperatures deep in the planet's atmosphere, may be starving the spot. Some scientists compare it to a wildfire running out of fuel. Without fresh turbulence to sustain it, the storm's fierce winds are slowly unraveling. Infrared data even hints that the spot is growing taller as it narrows, like toothpaste squeezed from a tube, stretching upward to compensate for its shrinking footprint. Yet the spot isn't going quietly. Recent Hubble images show tendrils of red gas spiraling outward, as if the storm is clawing at Jupiter's atmosphere to stay alive. And there's a tantalizing mystery: the color. The spot's famous hue, somewhere between brick and salmon, may come from chemicals like ammonium hydrosulfide, dredged up from Jupiter's depths by the storm's churn. As the vortex weakens, its color has faded, turning more peach than scarlet. But in 2019, astronomers spotted fresh red flakes breaking off, suggesting the storm might be recycling its own pigments, fighting to maintain its identity. The big question: is this the end? Some models predict the spot could vanish within decades, collapsing into a dull ripple. Others argue it might stabilize, settling into a smaller but equally fierce cycle. There's precedent. Jupiter's atmosphere birthed three white ovals in the 1930s that later merged into a single storm, proving these systems can evolve unpredictably. If the spot does disappear, it'll mark the close of a celestial era, leaving Jupiter's face strangely blank. But here's the twist: even if it fades, the spot's legacy will endure. Studying its slow demise helps scientists understand gas giants across the galaxy, how storms ignite, persist, and eventually die in alien atmospheres. And who knows, maybe somewhere beneath Jupiter's clouds, the next great red spot is already stirring, waiting for its turn to dominate the skies of the solar system's king. Until then, we're witnessing a cosmic spectacle, the slow unraveling of a storm that's outlasted empires, a reminder that even the mightiest forces in the universe are fleeting. Imagine a planet where the ground beneath your feet isn't rock or ice, it's diamond. Meet 55 Cancri E, a scorching hellscape orbiting so close to its sun that a single year flashes by in just 18 Earth hours. This isn't some sci-fi fantasy. It's a real exoplanet 4 times wider than Earth, and thanks to its carbon-heavy composition, scientists suspect its core could be a glittering sea of compressed diamond. Here's why this world is a cosmic jeweler's dream. Most planets form from the same stardust as their stars, rich in silicon and oxygen. But 55 Cancri E orbits a star with twice the carbon of our Sun, meaning its building blocks were more like cosmic coal than Earth's sandy crust. Under the crushing pressures of the planet's interior, think millions of times stronger than our deepest ocean trenches, that carbon crystallizes into diamond. Some models suggest its mantle could be hundreds of miles thick with the stuff, a vast molten treasure chest that would make any gem merchant's head spin. But don't pack your mining gear just yet. The surface is a blistering nightmare, reaching temperatures over 4,000 degrees Fahrenheit, hot enough to vaporize diamonds into graphite. There's no solid ground to stand on, just a superheated haze of carbon monoxide and hydrogen cyanide swirling above that diamond heart. And if the heat doesn't kill you, the gravity will. 55 Cancri E is so dense that a human weighing 150 pounds on Earth would feel like they were carrying 400 pounds here. What's wild is how this planet formed. Scientists think it might have started as a gas giant like Jupiter, only to have its atmosphere stripped away by its star's fury, leaving behind a naked, carbon-rich core. Or perhaps it migrated inward from colder reaches of its system, dragging icy hydrocarbons into the inferno where they shattered and reformed as diamonds. Either way, it's a reminder of how alien planetary chemistry can be. Our solar system's rules don't apply everywhere. And here's the kicker: 55 Cancri E might not be alone. Other carbon-heavy worlds likely exist, some even richer in diamond-forming material. Studying them could rewrite our understanding of planet formation, proving that the universe isn't just diverse, it's lavish, crafting worlds from materials we'd consider priceless. So next time you admire a diamond ring, remember, somewhere in the cosmos, there's a whole planet where that sparkle isn't rare, it's the bedrock. You might think the coldest place in the universe is some distant, sunless void between galaxies, but shockingly, it's right here in a lab on Earth. Scientists have created temperatures just a few billionths of a degree above absolute zero, colder than even the cosmic background radiation that permeates deep space. These ultra-frigid conditions aren't found in nature. They're engineered using bizarre states of matter called Bose-Einstein condensates, where atoms lose their individuality and behave like a single, wave-like superatom. To understand how this works, picture absolute zero, the theoretical temperature where all atomic motion stops, roughly minus 459.67 degrees Fahrenheit. Space itself isn't that cold. The ambient heat from the Big Bang keeps it at a balmy minus 455 degrees. But in labs like NASA, a cold atom lab on the International Space Station, physicists use lasers and magnetic fields to slam the brakes on atoms, slowing them until they're almost motionless. It's like trying to stop a speeding train by catching every single passenger with a microscopic net. The magic happens when atoms chilled to these extreme temperatures collapse into a Bose-Einstein condensate. At this point, quantum effects take over. Atoms overlap and synchronize, acting less like particles and more like ripples in a shared pond. This state was predicted by Satyendra Nath Bose and Albert Einstein a century ago, but it wasn't until 1995 that researchers finally created one using rubidium atoms. The breakthrough earned them a Nobel Prize and opened a window into the quantum world. Why go to such lengths to freeze atoms? These condensates let scientists simulate conditions near black holes or test quantum mechanics on visible scales. In space, microgravity allows even colder temperatures by eliminating the interference of Earth's gravity, letting condensates exist longer for study. Some experiments have chilled matter to within 1/1000th of a degree above absolute zero, a record that keeps getting shattered. Here's the cosmic irony: the universe's coldest spots are human-made, fleeting, and vanish the moment equipment shuts off. Yet they hint at a deeper truth that the boundaries of temperature aren't set by nature, but by our ingenuity. So while space may be vast and frigid, the true cold frontier isn't out there. It's in a lab where scientists push the limits of how slow and how strange matter can get. Imagine watching the sun dip below the horizon on Mars, only instead of Earth's fiery oranges and pinks, the sky erupts in an otherworldly blue. This isn't some artist's rendition. It's real footage captured by NASA rovers, showing sunsets that look like they're ripped from a sci-fi dreamscape. While our home planet treats us to warm, golden twilight, Mars serves up a cool, ethereal glow, painting its barren deserts in shades of sapphire and aqua. The secret lies in the Martian dust, fine as powdered chalk and constantly swirling in the thin atmosphere. On Earth, sunsets turn red because our thick air scatters blue light during the day, leaving longer red wavelengths to dominate at dusk. But Mars flips the script. Its dust particles are just the right size to scatter red light outward, letting the shorter blue wavelength push through to your eyes. It's like the difference between shining a flashlight through fog, Earth's sunset, versus through a glass of milky water, Mars's version. The result is a twilight that feels eerily inverted, as if the planet itself got the colors backwards. Here's what's even wilder: the blue isn't uniform. Depending on the dust density, the sky can shift from pale robin's egg near the horizon to a deeper cobalt directly around the sun. Rover images show the solar disk appearing almost white, haloed by that surreal azure glow. And because Mars' atmosphere is 100 times thinner than Earth's, the transition from day to night is lightning fast, no lingering hues, just a swift, vivid wash of color before darkness swallows the landscape. But why does this matter beyond its sheer beauty? Martian sunsets are more than a cosmic light show. They're a weather report. The intensity of the blue reveals how much dust is floating overhead, helping scientists track storms and seasonal changes. A deeper blue means clearer air, while a muted tone hints at distant dust clouds. Future colonists might one day use these daily color shifts to predict incoming storms, just like sailors once read the sky's red hues at dawn. And think about this: when the first humans stand on Mars, they'll witness something no Earthling has ever seen naturally, a blue sunset with their own eyes. No filters, no simulations, just the raw, uncanny beauty of light bending through an alien sky. It's a reminder that even the most familiar phenomena like day's end can transform utterly on another world. So next time you watch the sun sink below your horizon, picture it happening in reverse on Mars, where twilight isn't an ending but a daily brushstroke of cosmic artistry. Pluto's calendar moves at a glacial pace, so slow that a single birthday party there would span 2.5 centuries back on Earth. This tiny world, smaller than our moon, takes 248 Earth years just to complete one lap around the sun. That's longer than the entire existence of the United States as a nation. But Pluto doesn't just amble along in a neat circle like the planets closer to the Sun. It carves a wild, lopsided path that swings it from icy isolation into the solar system's bustling suburbs before yanking it back out into the void. What makes Pluto's orbit so extreme? It's all about eccentricity. While most planets trace nearly circular paths, Pluto's orbit resembles a squashed oval, stretching so far that at its closest approach, it actually dips inside Neptune's orbit for 20 years. Yes, Pluto was closer to the Sun than Neptune from 1979 to 1999. Then it embarks on a staggering 124-year journey back to the frozen outer reaches, where sunlight is so faint you could blot it out with a pinprick held at arm's length. This elongated dance creates seasons unlike anything in the inner solar system. When New Horizons flew by in 2015, Pluto was nearing its closest point to the Sun, causing its thin nitrogen atmosphere to briefly puff up like a balloon. But as it retreats, that atmosphere will slowly freeze solid, snowing back onto the surface in a glittering layer of ice. Temperatures, already hovering around -380 degrees Fahrenheit, will plunge even further, turning the dwarf planet into an even darker, more frigid world. The real kicker, Pluto's day is just 6.5 Earth days long, meaning its year contains over 14,000 Plutonian days. Imagine celebrating New Year's Eve every 6 days while waiting 2.5 centuries for spring to arrive. Its axial tilt, a steep 120 degrees, adds another bizarre twist. Some regions spend decades in permanent sunlight, followed by equal stretches of unbroken darkness. But why does Pluto orbit this way? Blame Neptune's gravitational tug. The two worlds are locked in a rhythmic resonance. For every 3 orbits Neptune completes, Pluto finishes 2, a cosmic synchronization that prevents collisions but amplifies Pluto's wild orbital swings. It's a stark reminder that even in the Kuiper Belt's frozen fringe, gravity writes the rules, sculpting paths that defy earthly intuition. And here's the haunting thought. No human has lived long enough to witness Pluto complete a single year since its discovery in 1930. By the time it finally circles back to where Clyde Tombaugh first spotted it, entire generations will have come and gone. That's the true scale of cosmic time, where a year isn't just a measure of seasons, but a silent testament to the universe's patience. Every year, without fail, the Moon packs its bags and moves a little farther away from Earth, about 1.5 inches to be exact. That might not sound like much, but over time it adds up. In 100 million years, our night sky will look noticeably different, with the Moon appearing smaller and dimmer, and the force behind this slow-motion escape. It's not some cosmic conspiracy, it's the same gentle tug that gives us ocean tides. Here's how it works. Earth's gravity locks the Moon in orbit, but the Moon's gravity also pulls back on Earth, stretching our planet ever so slightly. This creates tidal bulges not just in the oceans, but in the solid ground beneath us. Because Earth rotates faster than the Moon orbits, those bulges actually get dragged ahead of the Moon's position. This off-center pull acts like a gravitational slingshot, transferring energy from Earth's rotation to the Moon's orbit, nudging it farther out. The math behind this is mind-bending. The Moon's retreat slows Earth's spin by about 2 milliseconds per century, meaning days were just 22 hours long back when dinosaurs roamed. Fossilized tidal records from ancient shellfish even confirm this, showing daily growth rings that align with shorter days in Earth's distant past. And the process won't stop until Earth and the Moon become tidally locked, facing each other like dancers frozen mid-embrace, with a day and a month lasting the same length. But don't panic, humanity will be long gone before the Moon's departure changes things drastically. Even in 1 billion years, it'll only be 15% farther away. Still, this slow drift has real consequences. Without the Moon's stabilizing pull, Earth's axial tilt could wobble chaotically, triggering wild climate swings. And those breathtaking total solar eclipses, they'll eventually become a relic of the past, as the moon's shrinking apparent size means it won't fully cover the sun anymore. What's fascinating is that this isn't unique to Earth. Mars' tiny moon Phobos is doing the opposite, spiraling inward due to tidal forces, and destined to either crash into the planet or shatter into a ring within 50 million years. Meanwhile, Jupiter's moons play a complex gravitational game, some drifting out while others fall closer. It's a reminder that even the most seemingly permanent celestial relationships are in constant, delicate flux. So the next time you gaze up at the moon, remember, it's not just a static fixture in the sky. It's a traveler inching away bit by bit, quietly rewriting Earth's future one tide at a time. Saturn's dazzling rings, those iconic cosmic halos that have mesmerized astronomers for centuries, are vanishing before our eyes, not in some distant future but right now. NASA Cassini spacecraft revealed the shocking truth. Saturn's gravity is actively devouring its own rings, pulling them downward as icy rain at a rate that could erase them entirely within 300 million years. That might sound like an eternity, but in cosmic terms, it's a blink, meaning we're witnessing the ring's final act, a slow-motion disappearance that's been unfolding since the age of dinosaurs. This celestial feast happens because Saturn's rings aren't solid. They're trillions of swirling ice chunks, some as small as dust grains, others as big as houses. The planet's gravity tugs at this debris, while ultraviolet light from the sun charges the particles, making them susceptible to Saturn's magnetic field. The result, a steady ring rain where ice particles spiral inward, vaporizing as they plunge into the planet's upper atmosphere at speeds topping 10,000 miles per hour. Cassini detected this downpour directly, enough material to fill an Olympic-sized swimming pool every 30 minutes, drizzling onto Saturn in a shimmering, doomed shower. But here's the twist: the rings might be even younger than we thought. Their pristine ice suggests they formed after the dinosaurs, possibly from a shattered moon or a captured comet that wandered too close and was torn apart by tidal forces. If that's true, Saturn's rings are more like a fleeting cosmic fashion statement than a permanent fixture, gracing the solar system for just a fraction of its history. The real mystery: why they're vanishing so fast. Some regions are losing material up to 10,000 times faster than expected, hinting at hidden processes like meteoroid impacts churning up extra debris or electromagnetic forces accelerating the rain. Even Saturn's seasons play a role. When the planet tilts its ring's edge onto the sun, shadowed ice clumps grow stickier, slowing the decay. But during Saturn's summer, sunlight heats the rings, revving up the destruction like a defrosting glacier. And don't assume this is unique to Saturn. Jupiter's faint rings might be the ghostly remnants of a once grand system, while Uranus's dark, narrow rings could be decaying just as quietly. It's a reminder that even the most breathtaking celestial features are temporary cosmic sandcastles waiting for the tide. So next time you gaze at Saturn through a telescope, savor the view. You're witnessing a vanishing masterpiece, a delicate dance of ice and gravity that future civilizations might only read about. The universe gives, and the universe takes away, sometimes right before our eyes. Astronauts stepping back inside after a spacewalk often report a bizarre scent clinging to their suits, a mix of seared steak, hot metal, and gunpowder that lingers in the airlock. This isn't some psychological quirk. It's the literal smell of space itself, absorbed by their gear during hours exposed to the vacuum. Sunita Williams described it as distinctly metallic, while others likened it to ozone after a thunderstorm or the acrid tang of welding fumes. The most poetic comparison, like the scent of a just extinguished match but with a weird electric sharpness underneath. So where does this otherworldly aroma come from? The culprit is polycyclic aromatic hydrocarbons, complex molecules that float between stars, clinging to astronaut suits like cosmic perfume. These PAHs form in the extreme conditions of space, where ultraviolet radiation fractures and reassembles simple atoms into pungent compounds. When astronauts repressurize the airlock, those molecules mingle with oxygen, triggering chemical reactions that release the signature burnt metal whiff. It's the equivalent of opening an oven door after baking, except instead of cookies, you're smelling the raw ingredients of the universe. But here's the twist: the smell changes depending on where you've been. Spacewalks near the ISS's solar arrays sometimes carry a faint whiff of singed electronics, likely from interactions with charged particles. Hubble repair crews in the 1990s reported an added note of charcoal, possibly from aged insulation exposed to decades of cosmic rays. And moonwalkers, their suits picked up that gunpowder scent from lunar dust, proof that every corner of space leaves its own olfactory calling card. The weirdest part: astronauts can't actually smell space in real time. Without air to carry scent particles, their noses go useless the moment they step outside. It's only when they return and their suits off-gas those trapped molecules that the aroma hits. Some compare it to taking off motorcycle gloves after a long ride and catching whiffs of gasoline and leather, a delayed sensory echo of the journey. Scientists take this seriously. At NASA Johnson Space Center, chemists analyze suit residue to identify these spaceborne compounds, which could reveal hidden dangers like corrosive substances that might damage equipment over time. There's even talk of bottling the scent for training simulations, helping new astronauts recognize the smell before their first mission. So next time you light a sparkler or catch the tang of a blown fuse, think of the astronauts unpacking their suits after a spacewalk, breathing in the essence of the cosmos. It's a reminder that space isn't just empty and silent, it's a vast chemical laboratory, simmering with invisible reactions that leave their mark on anyone who dares to step outside. And for those few who have experienced it, that metallic bite is more than a smell, it's the scent of adventure itself. When the Hubble Space Telescope launched in 1990, it was supposed to revolutionize astronomy, giving us crystal-clear views of the cosmos free from Earth's blurry atmosphere. But within weeks, scientists realized something was catastrophically wrong. The first images Hubble sent back were fuzzy, like a camera with smeared lenses. The culprit, a mirror polished too perfectly but to the wrong shape. Due to a measuring error during manufacturing, its curvature was off by just 2 microns, about 1/50th the width of a human hair. That microscopic flaw scattered light, turning what should have been razor-sharp cosmic portraits into blurry blobs. The irony was crushing. Hubble, NASA, a $2.5 billion flagship, was orbiting Earth as a near-sighted telescope. Comedians mocked it as NASA, a myopic marvel, while astronomers watched their research plans evaporate. The mirror couldn't be replaced, it was permanently welded inside Hubble's barrel. But engineers didn't surrender. They devised an audacious fix: cosmic eyeglasses. Enter COSTAR, the corrective optics space telescope axial replacement. This washing machine-sized contraption housed 10 coin-sized mirrors designed to counteract Hubble's flaw by bending light precisely opposite the error. Installing it required one of the most complex spacewalks ever attempted. In December 1993, the Space Shuttle Endeavour rendezvoused with Hubble, and astronauts spent 5 back-to-back spacewalks performing what amounted to orbital brain surgery. One team replaced Hubble's camera with a new model containing built-in corrections, while another painstakingly slid COSTAR into place like a contact lens for a giant eye. The tension was unbearable. If the mirrors were misaligned by even a fraction of a millimeter, Hubble would remain useless. But when the first corrected images flashed onto monitors, the room erupted. Distant stars snapped into perfect pinpoints, and spiral galaxies revealed intricate arms choked with newborn stars. The repair wasn't just a success, it transformed Hubble into the instrument of its original promise. What's astonishing is how adaptable the fix was. CoStar wasn't part of Hubble's original design. It was invented on the fly, proving that even billion-dollar mistakes could be solved with ingenuity. Later upgrades gradually made CoStar obsolete. New instruments had corrections built in, but its legacy endures. That daring mission didn't just save Hubble, it set a precedent for fixing spacecraft in situ, paving the way for future repairs like the James Webb Space Telescope's unfolding mirrors. And here's the kicker: without that initial flaw, we might never have gotten Hubble's most iconic images. The crisis forced engineers to develop sharper calibration techniques and more resilient hardware, ultimately making the telescope better than its original specs. Sometimes the universe's greatest discoveries come from fixing its most embarrassing mistakes. Mercury, the tiny planet closest to the Sun, seems like the last place you'd expect to find ice. Its dayside temperatures soar to 800 degrees Fahrenheit, hot enough to melt lead. Yet hidden in the shadows of its polar craters, spacecraft have uncovered vast deposits of water ice, gleaming like cosmic frost in permanent darkness. This discovery shattered every expectation about the scorched world, proving that even in the solar system's most inhospitable corners, water finds a way to survive. The first clues came in the 1990s when Earth-based radar scans detected strangely bright reflections near Mercury's poles, signatures that screamed ice. But how could frozen water exist just 36 million miles from the Sun? The answer lies in Mercury's extreme tilt, or rather, its lack of one. Unlike Earth, which wobbles on its axis, Mercury stands almost perfectly upright. This means its polar regions never tilt toward sunlight, leaving some crater floors in eternal shadow. These cold traps plunge to -370 degrees Fahrenheit, creating natural freezers where ice can persist for billions of years. NASA's Messenger mission confirmed the unthinkable in 2012. Flying over Mercury's North Pole, its instruments mapped ice deposits thick enough to blanket Washington, D.C. under 2.5 miles of frozen water. Some craters held enough ice to fill 20,000 Olympic swimming pools, astonishing for a planet where the sunny side could vaporize a glacier in minutes. Even crazier, the ice isn't pure. It's mixed with dark organic compounds, likely delivered by comets that smashed into Mercury over eons, painting the frozen reservoirs with a tar-like coating that helps insulate them from the surrounding furnace. Here's the twist: Mercury's ice isn't just a scientific curiosity, it's a time capsule. Because the planet has no atmosphere to erode the surface, that ice could be pristine material from the early solar system, untouched since the era when comets rained water across the inner planets. Studying its chemical fingerprints might reveal how Earth got its oceans, or whether the ingredients for life hitched rides on these ancient ice deliveries. And the implications don't stop there. If Mercury, of all places, can hoard ice, then what about other seemingly dry worlds? Astronomers now scrutinize lunar polar craters and asteroid surfaces with renewed urgency, wondering where else water might lurk in the shadows. For future explorers, these hidden caches could be lifesavers, literally. Ice means drinking water, breathable oxygen, and even rocket fuel if split into hydrogen and oxygen. Mercury's frozen vaults are a reminder that in space, the most valuable treasures often hide in the unlikeliest places. So next time you picture Mercury as a barren, sun-blasted rock, remember, its poles are silent ice kingdoms holding secrets older than the dinosaurs. The universe loves a good paradox, and this tiny planet delivers. A world where fire and ice exist side by side, separated by nothing more than a crater's edge. Most comets are dirty snowballs, trailing plumes of water vapor and dust, but in 2015, astronomers stumbled upon something far more intriguing: a comet spewing alcohol into space. Comet Lovejoy, a Christmas visitor that year, wasn't just throwing off the usual mix of frozen gases. As it swung around the Sun, telescopes detected something unexpected in its shimmering tail: ethyl alcohol, the same stuff in your favorite beer or whiskey, gushing out at a rate that could have filled 500 bottles every second. This wasn't some cosmic brewery. The alcohol was a byproduct of complex chemistry baked into Lovejoy's icy core over billions of years. Sunlight vaporized ancient ices, releasing molecules like ethanol, glycolaldehyde, a simple sugar, and even complex organic compounds into space. Scientists estimate Lovejoy's alcohol output was staggering, around 20,000 tons of the stuff during its closest approach. That's enough to keep every bar on Earth stocked for decades, all from a single comet barely 3 miles wide. What makes this discovery so fascinating isn't just the novelty of a tipsy comet, it's what it tells us about the raw ingredients of the cosmos. Lovejoy's cocktail of molecules mirrors those found in star-forming regions, suggesting that the building blocks of life's chemistry might be scattered across the universe, hitching rides on these icy wanderers. Some researchers speculate comets could have seeded young planets with organic material, delivering not just water, but the molecular precursors to amino acids and other life-essential compounds. And here's the kicker: Lovejoy isn't alone. Other comets like Hale-Bopp and Hyakutake have been caught releasing methanol and formaldehyde, hinting that alcohol production might be a common feature of these cosmic snowballs. While we're not about to find a comet spewing aged bourbon, the presence of ethanol, a relatively complex molecule, suggests the universe has a knack for organic chemistry, even in the freezing void of deep space. But before you picture astronauts harvesting comet tails for interstellar happy hour, remember, space isn't that kind. Lovejoy's alcohol is hopelessly diluted, mixed with toxic gases like cyanide and ammonia, and spread across millions of miles of vacuum. Still, this tipsy traveler offers a tantalizing clue. If comets carry such rich chemistry, could they have been the galactic bartenders that served up Earth's first organic molecules? It's a sobering thought that the origins of life might owe a toast to a drunken comet's long-ago flyby. Uranus doesn't just orbit the Sun, it rolls around it like a drunken cosmic bowling ball, tipped sideways at a jaw-dropping 98-degree angle. Unlike every other planet in our solar system, which spin more or less upright as they circle the Sun, Uranus is practically doing cartwheels, with its north pole sometimes pointing almost directly at our star. This bizarre tilt gives Uranus the most extreme seasons imaginable. Each pole gets 42 straight years of brutal sunlight, followed by 42 years of uninterrupted darkness, while the equator experiences cyclically bizarre sunrises and sunsets that defy earthly logic. So how did Uranus end up in this topsy-turvy state? The leading theory is as dramatic as it sounds: a cataclysmic collision with an Earth-sized object in the early days of the solar system. Picture a rogue protoplanet smashing into Uranus with such force that it literally knocked the planet sideways, sending it spinning like a top that's lost its balance. The impact might have been so violent that it also explains Uranus's unusually lopsided magnetic field, which is tilted 60 degrees from its axis and offset from the planet's center. Imagine holding a compass that doesn't point north instead. It wobbles erratically thanks to a planetary trauma billions of years old. The consequences of this tilt are as strange as they are spectacular. During solstices, when one pole faces the Sun, the atmosphere over that hemisphere heats up dramatically, generating storms that rage across latitudes normally accustomed to cold. Meanwhile, the opposite pole plunges into a deep freeze, its weather systems grinding to a halt in the endless night. Then, as Uranus continues its 84-year orbit, the roles reverse like a slow-motion game of celestial tag where the stakes are hurricane-force winds and temperature swings that would make Earth's most extreme weather look tame. But here's the real kicker. Uranus's moons and rings are dragged along for the ride, orbiting around its tilted equator like guests at a never-ending dinner party where the table keeps flipping sideways. This means their paths are perpendicular to the plane of the solar system, creating orbits that look more like bullseyes than neat circles. Even the sunlight hitting these moons is bizarre. Imagine a world where the sun spirals in a corkscrew path across the sky, sometimes hovering just above the horizon for years before finally dipping below. What's incredible is that we might never have uncovered these secrets without Voyager 2's flyby in 1986, still the only spacecraft to visit this icy oddball. Its images revealed a nearly featureless blue-green world, its atmosphere smoothed by extreme cold, but stirred by winds that somehow blow faster than the planet rotates. More recent Hubble observations have caught glimpses of colossal storms and bright methane clouds erupting as seasons shift, proving Uranus is far from the boring ice giant it was once dismissed as. Uranus's tilt isn't just a planetary quirk, it's a window into the solar system's violent youth. While Earth and its neighbors settled into orderly spins, Uranus became a cautionary tale of cosmic chaos, a reminder that even the mightiest worlds can be knocked sideways by the universe's whims. And as astronomers discover more tilted exoplanets in distant systems, Uranus stands as a local example of just how wild and unpredictable planetary formation can be. So next time you picture the solar system's orderly dance, remember the outlier rolling around the edges, flipping the script on what a planet can be. Mars is home to a volcano so massive it defies earthly comprehension. Olympus Mons, a titan that makes Mount Everest look like a speed bump. This gargantuan shield volcano towers 16 miles above the Martian surface, nearly 3 times the height of Everest, with a base so wide it could swallow the entire state of Arizona. If you stood at its summit, the curvature of Mars would be visibly distorted at the horizon, and the volcano's slopes would stretch so gradually that you wouldn't even realize you were climbing. What makes Olympus Mons so staggeringly large? The answer lies in Mars' lack of tectonic activity. On Earth, shifting plates constantly recycle the crust, preventing any single volcano from dominating for too long. But Mars is a one-plate planet. Its crust remains stationary, allowing lava to pile up in the same spot for billions of years. Think of it like pouring pancake batter onto a griddle that never moves. Each eruption adds another layer, spreading outward in smooth, gentle slopes rather than steep, explosive peaks. Over time, this process created a volcano so vast its caldera, the bowl-shaped depression at the top, could fit 3 Manhattans stacked side by side. The sheer scale of Olympus Mons isn't just about height. Its footprint covers an area roughly the size of France, with cliff edges taller than the Grand Canyon encircling parts of its base. These cliffs, some 6 miles high, likely formed as the volcano's weight caused the Martian crust to sag, creating sheer drop-offs that dwarf anything on Earth. And while it's considered dormant today, geologists suspect its last eruption might have occurred as recently as 25 million years ago, a blink in cosmic time. But here's the real mind-bender. Olympus Mons isn't alone. Mars boasts 3 other megavolcanoes in the Tharsis region, each large enough to be the biggest on Earth. Together, they form a volcanic province so heavy it may have altered the planet's rotation, shifting Mars' axis over eons like a poorly balanced washing machine. Some scientists even speculate these eruptions pumped enough greenhouse gases into the atmosphere to briefly warm ancient Mars, creating fleeting periods where liquid water could flow. Yet for all its grandeur, Olympus Mons holds a quiet irony. Its eruptions were likely slow and oozing, not the fiery explosions we associate with volcanoes like Vesuvius or Krakatoa. Picture thick, syrupy lava creeping across the landscape at walking speed, piling up in layers over millennia. This gentleness is what allowed it to grow so large, a testament to patience on a planetary scale. What's haunting is that we might never see its like again. Without active tectonics, Olympus Mons represents a relic of a bygone era, a monument to the raw, unfettered power of Mars' volcanic youth. Future colonists gazing up at its slopes won't just be staring at a mountain. They'll be witnessing a frozen moment in time where fire built an edifice so vast it redefined the very skyline of a world. Here's something you've probably never considered about life in space. Astronauts can't enjoy a simple, satisfying burp. Back on Earth, gravity does the quiet work of separating liquids and gases in your stomach, letting gas bubbles rise to the top for a clean release. But in microgravity, that process falls apart literally. Without gravity to sort things out, gas and fluid stay trapped in a chaotic mix, turning what should be a harmless burp into a messy, unpredictable event astronauts call wet burps. Imagine taking a sip of soda and feeling the bubbles fizzing inside you, only to discover they won't budge upward. When astronauts try to burp, there's no guarantee it'll be just gas. The result, a stomach-churning blend of half-digested food and air that's more like a hiccup gone wrong. Veteran spaceflyer Scott Kelly described it as a weird, gurgly sensation, while others compare it to the queasy feeling of reflux but with zero relief. This isn't just uncomfortable, it's a genuine hazard. In the confined space of a spacecraft, floating vomit droplets are a biohazard, and the constant sloshing of unbubbled gas can lead to painful bloating. That's why astronauts carefully avoid carbonated drinks and foods that trigger gas, like beans or broccoli. Even something as simple as a fizzy drink could turn into a regretful decision when there's no gravity to help you expel the bubbles gracefully. The science behind this is surprisingly complex. On Earth, buoyancy forces gas to rise, creating a neat layered system in your stomach. In space, that hierarchy collapses. Fluids and gases form a jumbled emulsion like a shaken soda bottle that never settles. Over time, the body adapts, sort of. Some astronauts report their digestive systems eventually adjust, producing fewer wet burps as missions progress. But for newcomers, it's an unwelcome rite of passage. Here's the kicker: this quirk of space biology has led to some creative engineering. Space agencies have experimented with carbonated drinks in special pressurized containers that force gas to stay dissolved until consumed. Even then, the experience is underwhelming. Impaired taste buds in microgravity make fizzy drinks taste flat, removing much of the appeal. Ultimately, astronauts learn to live with it, trading earthly pleasures like a crisp soda for the surreal privilege of floating among the stars. But there's a silver lining. Understanding these digestive challenges helps scientists prepare for longer missions like trips to Mars. Figuring out how to keep astronauts comfortable and safe from stomach acid mishaps could be key to maintaining crew morale over months or years in space. So the next time you enjoy a guilt-free burp after a meal, take a second to appreciate gravity's unsung role in keeping things tidy. In space, even the smallest bodily functions become a reminder of how deeply we're wired for life on Earth. The Milky Way isn't just a glittering river of stars. It's a cosmic heavyweight tipping the scales at an almost incomprehensible 1.5 trillion times the mass of our Sun. That staggering number comes from the European Space Agency's Gaia mission, which spent years painstakingly mapping the motions of billions of stars to solve one of astronomy's oldest puzzles: just how much does our galaxy actually weigh? The answer reshaped everything we thought we knew about our galactic home. To grasp how scientists pulled off this measurement, picture the Milky Way not as a static snapshot, but as a dynamic, swirling dance. Stars don't orbit randomly. Their speeds reveal the gravitational pull of all the mass around them, both visible stars and the invisible dark matter that makes up most of the galaxy's bulk. Gaia's breakthrough was tracking the three-dimensional movements of globular clusters, dense groups of ancient stars orbiting the Milky Way's outskirts. By analyzing how fast these clusters whip around the galaxy's center, astronomers could reverse engineer the gravitational forces at play, like weighing a spinning merry-go-round by watching how kids cling to its edges. The real surprise wasn't the total mass, but where it's hiding. Only about 15% comes from stars, gas, and dust, the glittering Milky Way we see in photos. The rest, an invisible halo of dark matter, a mysterious substance that doesn't emit light but tugs on everything with its gravity. This shadowy scaffolding stretches far beyond the galaxy's visible disk, creating a gravitational footprint 10 times wider than the span of its spiral arms. Here's what's wild. Weighing a galaxy from the inside is like trying to measure your own weight while standing on a trampoline. Gaia's Team Cross checked their results with Hubble's observations of hyperfast stars flung outward by the galaxy's spin, acting like cosmic speedometers. Combined, these techniques revealed the Milky Way is heftier than previously thought, 50% more massive than early estimates, placing it on par with our neighboring Andromeda galaxy rather than lagging behind. But why does this number matter? Mass dictates destiny. A heavier Milky Way means stronger gravity, which influences how galaxies collide, how stars form, and even how fast our solar system orbits the galactic core. We're currently cruising at 514,000 miles per hour, by the way. It also raises tantalizing questions. If dark matter dominates our galaxy, what strange particles compose it, and how does its distribution shape the universe's expansion? The irony is poetic. For centuries, we've gazed at the Milky Way's glowing band, unaware that most of it is invisible. Gaia's measurement doesn't just give us a number, it reveals how much we're not seeing, a humbling reminder that the universe's grandest structures are built on shadows. So next time you look up at the night sky, remember, you're not just staring at stars, you're glimpsing the fingerprint of something far greater, a hidden architecture holding the galaxy together, 1 trillion suns at a time. Some of the universe's most unusual stars don't blaze with heat at all, they're cooler than a brisk autumn day. Meet Y-class brown dwarfs, the cosmic oddballs that defy everything we expect from stellar objects. These failed stars, too massive to be planets yet too small to ignite fusion in their cores, simmer at temperatures that could make you sweat less than your own body. The coldest known example, Y0855, chills at a bone-numbing -10 degrees Fahrenheit colder than a winter night in Antarctica and only slightly warmer than a household freezer. What makes these objects so bizarre isn't just their temperature, it's how they blur the line between star and planet. Brown dwarfs form like stars, collapsing from vast clouds of gas, but they lack the mass to sustain the nuclear reactions that power true stars. Instead, they glow faintly with residual heat from their formation, slowly fading like embers in a cosmic campfire. The Y-class dwarfs are the coldest of this already strange group, so frosty that their atmospheres host clouds of water vapor, not as steam but as ice crystals swirling in alien skies. Here's where it gets surreal. If you could stand on one, ignoring the crushing gravity and lack of solid ground, you might not even realize you were on a star. The sunlight here would be an eerie, dim glow, barely brighter than a full moon on Earth. Their spectra reveal molecules like ammonia and methane, substances you'd expect in a gas giant's atmosphere, not a celestial body born from stellar nurseries. Some even have weather systems, with violent winds whipping these exotic clouds into storms that would dwarf Jupiter's great red spot. The discovery of these lukewarm stars forced astronomers to rethink their definitions. Before the 1990s, nobody thought objects this cool could exist. Then infrared telescopes like WISE and Spitzer began peeling back the cosmic curtains, spotting these shadowy orbs lurking in interstellar space, often drifting alone, untethered to any solar system. Their faintness makes them devilishly hard to study. WISE 0855, for instance, emits barely any visible light, requiring painstaking analysis of heat signatures to confirm its existence. Yet their coolness is a goldmine for science. White dwarfs serve as natural laboratories for understanding planetary atmospheres, offering clues about gas giants orbiting other stars. Some researchers speculate they might even harbor habitable zones not for surface life, but for hypothetical moons with thick atmospheres trapping warmth. And because they're so long-lived, barely changing over billions of years, they act as cosmic time capsules, preserving conditions from the early universe in their chilly embrace. So next time you step outside on a chilly night, look up. Hidden in the darkness are stars that wouldn't warm your hands, celestial phantoms rewriting the rules of what it means to shine. The universe, it seems, has a flair for irony, crafting stars so cold they make winter feel like a sauna. Astronaut Scott Kelly returned from his year-long mission aboard the International Space Station with more than just breathtaking photos of Earth. His very DNA had changed. Scientists analyzing blood samples taken before, during, and after his stay made a startling discovery. The protective caps on his chromosomes, called telomeres, had grown longer in space. These tiny biological timekeepers, which normally shorten with age and stress, seem to defy expectations by stretching out like cosmic accordions while orbiting Earth. Telomeres act like the plastic tips on shoelaces, preventing our genetic material from fraying over time. On Earth, factors like poor sleep, chronic stress, and even mental health struggles can accelerate their shortening, a process linked to aging and diseases like cancer. But in microgravity, Kelly's telomeres didn't just resist deterioration. They flourished, becoming more elongated than his twin brother Mark's back on Earth. The finding sent shockwaves through the scientific community, challenging long-held assumptions about how space affects human biology at the most fundamental level. The leading theory, spaceflight might temporarily boost the activity of telomerase, an enzyme that rebuilds these chromosomal buffers. Radiation exposure, circadian rhythm disruptions, and the unique physical stresses of microgravity could trigger survival mechanisms that dial up cellular repair. It's as if Kelly's body, confronted with an alien environment, went into biological overdrive to protect its genetic blueprint. But this cosmic perk didn't last. Within months of returning to Earth, his telomeres rapidly shortened, settling back near pre-flight length. That whiplash effect hints at how delicately balanced our biology is, adapting to extremes only to snap back when gravity reasserts its pull. What's truly bizarre is how this contradicts other known space hazards. Astronauts typically face accelerated aging markers like bone density loss, muscle atrophy, and vision changes from fluid shifts in microgravity. Yet here was evidence that at the cellular level, space might briefly press pause on one aspect of aging. Researchers scrambled to reconcile these findings. Was it a fluke? Or did microgravity selectively activate anti-aging pathways while wreaking havoc elsewhere? The implications are profound. If scientists can isolate what caused this telomere extension, it might unlock new therapies for Earth-bound conditions tied to cellular aging. Imagine harnessing space's strange biological effects to help cancer patients or slow degenerative diseases. But there's a dark side too. Kelly's telomeres didn't just normalize post-flight. Some became shorter than before his mission, suggesting possible long-term genomic instability from space's extreme conditions. This paradox captures the dual nature of space travel, a place where the human body can behave in ways that seem miraculous and alarming in equal measure. As we prepare for multi-year missions to Mars, understanding why telomeres stretch in orbit and whether that's ultimately beneficial or harmful becomes critical. For now, Kelly's elongated DNA remains one of spaceflight's most tantalizing mysteries, proving that even our genes aren't immune to the universe's transformative power. Saturn's North Pole isn't just another swirling storm, it's a geometric enigma, a near-perfect hexagon wide enough to fit 4 Earths inside its boundaries. This 6-sided jet stream, first spotted by Voyager in the 1980s and later studied in stunning detail by Cassini, defies every expectation of how planetary weather should behave. Unlike the chaotic cyclones of Jupiter or the vortexes of Earth's poles, Saturn's hexagon is a mesmerizingly precise structure, with razor-straight sides each longer than our planet's diameter, rotating in sync with the gas giant's deep interior. What keeps this cosmic polygon intact? The leading theory involves something called Rossby waves, massive atmospheric disturbances that ripple through fluids under rotation. On Earth, these waves help shape weather patterns like the jet stream, but Saturn's rapid spin a day that lasts just 10.5 hours amplifies them into a stable, self-reinforcing shape. Picture stirring a cup of tea with a spoon. Under certain speeds, the swirling liquid forms geometric patterns, now scaled at up to planetary dimensions, with winds screaming at 220 miles per hour along the hexagon's edges, and you've got a rough analogy for this phenomenon. But here's the twist: laboratory experiments can't fully replicate it. When scientists try to simulate the hexagon in rotating tanks of fluid, they often get multiple polygons or shapes that flicker unpredictably. Saturn's version, by contrast, has persisted for at least 40 years, possibly centuries, without distorting. Some researchers suspect deeper forces are at play, like interactions between Saturn's jet streams and its internal heat, which might act as an invisible scaffold holding the hexagon rigid. Others speculate the shape is an illusion, a standing wave pattern created by overlapping atmospheric oscillations, like the symmetrical nodes on a vibrating drumhead. The hexagon's interior is just as strange. Infrared images reveal it towers 60 miles above Saturn's cloud tops, with layers of haze stacked like a wedding cake. During the planet's long polar winter, the hexagon acted as a barrier, trapping a colossal cyclone at its center like a cosmic snow globe. When sunlight finally returned, Cassini captured the hexagonal border glowing golden, while the storm inside churned with filaments of gas resembling a celestial spiderweb. And then there's the color mystery. Unlike the rest of Saturn's pastel bands, the hexagon's core shifts hues, turning from blue to gold and back as seasons change over Saturn's 29-year orbit. This suggests chemistry we don't yet understand, possibly involving ultraviolet light breaking apart atmospheric molecules to create exotic compounds. The hexagon's precision haunts astronomers because it hints at hidden order in chaos. Gas giants weren't supposed to have such clean geometries. Their turbulence should erase any rigid shapes. Yet Saturn's pole stands as a testament to nature's ability to balance forces in ways that still elude our models. It's a reminder that even in the swirling maelstrom of a gas giant's atmosphere, the universe has a flair for the mathematical, etched not in equations, but in hurricane force winds and freezing clouds of ammonia. Perhaps the most humbling thought: this hexagon wasn't meant for us. Without spacecraft to image Saturn's poles, it would have remained invisible, a secret locked in perpetual darkness. Its existence challenges us to rethink what's possible in alien skies, and to wonder what other breathtaking patterns might be hiding in plain sight, waiting for the right vantage point to reveal them. The moon isn't the dead, silent world it appears to be. It shakes. Unlike Earth's quakes, which rumble from shifting tectonic plates, moonquakes are born from entirely alien forces. The gravitational tug of war with Earth, the chilling contraction of a cooling interior, and even the occasional meteorite slamming into the surface. Apollo astronauts left seismometers behind in the 1970s, and what they recorded was startling. Some tremors lasted 10 times longer than anything on our planet, vibrating the lunar crust like a struck gong for over an hour. These quakes come in 4 flavors, each more peculiar than the last. The most common are deep moonquakes, centered 400 miles below the surface, triggered by Earth's tidal forces stretching and squeezing the moon like a stress ball. Imagine our planet's gravity flexing the moon's rigid interior every 2 weeks as orbits align, generating hundreds of tiny quakes in predictable cycles. Then there are shallow thermal moonquakes caused by the brutal temperature swings between lunar day and night. The surface bakes at 260 degrees Fahrenheit at noon, then plummets to -280 at night, making the crust crack and pop like an overheating pavement. But the real showstoppers are the impact quakes. When meteorites, even small ones, smash into the moon's unprotected surface, the energy ripples through the ground with unnerving efficiency. Without an atmosphere to slow or burn up incoming space rocks, every impact is a direct hit, sending seismic waves racing through the dry, brittle regolith. The Apollo instruments caught one particularly violent impact in 1972, when a 1-ton asteroid struck at 40,000 miles per hour, shaking the moon for 3 hours. The strangest of all, artificial moonquakes. After dropping their lunar modules onto the surface, Apollo astronauts deliberately crashed their spent rocket stages into the moon to study the seismic echoes. These human-made tremors revealed something eerie. The moon's upper layers are a shattered mess of rubble, leftovers from billions of years of asteroid bombardment, while deeper down, the rock is strangely dry, devoid of water or molten layers that would dampen vibrations. It's why moonquakes resonate so long. There's nothing to absorb the energy. Here's what's haunting. These quakes could be a nightmare for future lunar bases. Unlike Earth, where quakes fade quickly, the moon's tremors build slowly, peak, then linger like a slow-rolling avalanche. A strong moonquake near a habitat could crack seals, destabilize slopes, or trigger landslides in the loose regolith. NASA even studied whether moonquakes might explain the transient lunar phenomena, mysterious flashes of light. Some astronomers swear they've seen, suggesting quakes could release trapped gases that ignite in sunlight. The ultimate irony, the moon's quakes are helping us understand Earth's own seismic past. Before plate tectonics began, our planet might have shaken much like the moon does today, its crust creaking under tidal forces and cooling stresses. Those Apollo seismometers, now long silent, gifted us a blueprint for how rocky worlds evolve. So next time you look up at that serene, cratered face, remember, beneath the dust, the moon is still alive, trembling with the echoes of its violent past and our own planet's forgotten youth. At the end of the 20th century, astronomers made a discovery so unsettling it rewrote the fundamental story of our universe. Not only is everything expanding, but that expansion is speeding up over time. This revelation came when two rival teams studying distant supernova found these cosmic explosions were dimmer than expected, meaning they were farther away than standard models predicted. The implications were staggering. Some mysterious force, now called dark energy, must be counteracting gravity's pull, driving galaxies apart at ever-increasing velocities. It was like throwing a ball in the air only to watch it shoot away faster instead of falling back down. Here's what makes dark energy so baffling. It accounts for roughly 68% of the universe's total energy content, yet we have no idea what it actually is. The leading theory suggests it's a property of space itself, Einstein's cosmological constant, resurrected where empty vacuum somehow generates repulsive gravity. But the math is wildly off. Quantum physics predicts a vacuum energy density 10 to the power of 120 times stronger than what we observe. This worst theoretical prediction in history hints that either our understanding of quantum fields is catastrophically wrong, or dark energy is something far stranger, like a dynamic field that evolves over cosmic time. The consequences of this accelerating expansion are existential. If it continues unchecked, distant galaxies will eventually vanish from view, their light stretched beyond detectability as space stretches faster than photons can traverse it. Tens of billions of years from now, civilizations arising in our local galactic group might see only blackness beyond Andromeda, with no evidence the broader universe ever existed. This heat-death scenario, where the cosmos becomes a cold, isolated graveyard, stands in stark contrast to earlier visions of a recollapsing Big Crunch. Yet dark energy isn't just a distant doom, it shapes the universe we see today. Its repulsive force stunted the growth of cosmic structures, preventing galaxy clusters from becoming as massive as they otherwise would. Without it, superclusters might have formed far earlier in cosmic history, potentially altering the conditions needed for life to emerge. Some theories even link dark energy to the universe's improbable luck in having just the right density for stars and planets to form, a haunting coincidence known as the fine-tuning problem. What's thrilling is how much we still don't know. Upcoming telescopes like ESA's Euclid and NASA's Nancy Grace Roman will map dark energy's influence with unprecedented precision, hunting for clues in the distortion of ancient light. Alternate theories like modified gravity or extra dimensions linger at the fringes, waiting to upend the paradigm entirely. The acceleration's discovery earned a Nobel Prize, but the real prize remains out there, understanding why our universe seems hellbent on flying apart and what that means for the ultimate fate of everything. For now, dark energy stands as cosmology's greatest unsolved mystery, a reminder that the cosmos still holds cards it hasn't shown us. From diamond rain on Neptune to the moon slowly fleeing Earth's embrace, the universe never runs out of ways to leave us speechless. Think about the absurdity of a planet where sunsets paint the sky blue, or a volcano so massive it distorts the horizon. Picture the astronauts who grew taller in space, only to shrink back under gravity's grip, or the eerie silence between stars where sound simply can't exist. And who could forget Saturn's vanishing rings crumbling into rain, or the Great Red Spot, a storm so ancient it's older than the telescope itself, now fading before our eyes. These aren't just facts, they're invitations to marvel. Every mission, every discovery peels back another layer of cosmic strangeness, proving reality outshines even our wildest sci-fi dreams. Whether it's Uranus rolling around the sun like a wayward billiard ball or a comet spouting enough alcohol to fuel an interstellar pub crawl, the universe thrives on the unexpected. So which fact blew your mind the most? Was it the hexagon spinning at Saturn's pole, defying every law of weather we know? Or perhaps the DNA of astronauts literally rewriting itself in orbit? Drop your favorite in the comments. We geek out over this stuff just as much as you do. And if you're craving more cosmic oddities, hit that subscribe button. Trust us, the universe has plenty more surprises up its sleeve, and we're just getting started. Until next time, keep looking up, because out there, the ordinary never stood a chance.